Good afternoon, everyone. Welcome to today's webinar, Managing Virus Threats with Proper Air Filtration. Our speaker today is Kyle Peterson, who is the Healthcare Segment Manager for Camfil USA. Kyle is responsible for cultivating, managing, and supporting Camfil hospital and healthcare clients throughout the US. Before we begin our webinar, I would like to remind the audience to please feel free to submit questions at any time during the session using the question answer feature on your webinar toolbar. We have invited a panel of industry experts to join us in this webinar, and they will be available to provide input throughout and to address questions from our participants. We have dedicated time after the presentation also for a Q&A session. If you happen to have any technical questions, please use the chat feature and your question will be addressed as soon as possible. And now I'd like to turn it over to our presenter, Kyle Peterson, who will also do the honors of introducing our panel of experts joining us today. Kyle, the floor is yours.
Well, thank you, Lynn. Hello, everyone, and thank you for joining us today. And a special thank you to Glenn Fisher and Alan Whitson for making this webinar possible. Before I get started, as Lynn mentioned, we are going to have a Q&A at the end of the session today. And so I wanted to briefly introduce our other panelists. In addition to myself, we have Mr. Kim Shin, who is the Senior Partner and Senior Sustainability Director at TLC Engineering. We also have Mr. Richie Stever, who's the Director of Operations and Maintenance at the University of Maryland Medical Center. And we also have our very own Mr. Kevin Wood, who is the VP of Sales and Marketing for Camfil USA. Camfil is partnering with AMFP today to deliver this webinar. So we hope you find the content to be both interesting and informative. I looked it up last Friday and there were 15,000 new cases of COVID nationally on that day across the United States. On January 8th of this year, we reached a peak of over 250,000 cases in a single day. So it appears as if the worst is behind us. And as the country opens up again, I, for one, am really looking forward to being able to do these types of events in person again. And in line with this idea of having large groups of people congregate safely, the topic for this presentation is managing virus threats with proper air filtration. Now, COVID-19 takes center stage here, but as we'll see, all of the viruses, bacteria, and other dangerous particles we encounter every day, particularly in healthcare settings, are similar in size to the SARS-CoV-2 virus. So the concepts I'm going to cover today apply equally to a post-pandemic world. Now, COVID-19 has impacted virtually every aspect of society across the globe, and it's difficult to imagine a silver lining around this disease, but poor indoor air quality is a root cause for many human illnesses. According to the American College of Allergy, Asthma, and Immunology, 50% of all illnesses are either caused by or aggravated by poor indoor air quality. It's a pervasive problem. And frankly, it's been a problem that's been largely ignored for far too long. So if this pandemic somehow generates a greater awareness around the importance of indoor air quality, and I believe it has, maybe there is an upside here that we can all benefit from in the future. So let's take a look at coronavirus from a filtration perspective. Now, here's that image that we're all way too familiar with by now, the SARS-CoV-2 virus with its distinctive crown-shaped protein spikes protruding from the envelope. Fun fact here, if you didn't already know it, corona is actually Latin for the word crown, which is where its name is derived from. Now, coronaviruses were first discovered in the 1960s, but have probably been causing illnesses in humans for thousands of years. They're responsible for common respiratory illnesses such as colds and pneumonia, along with mild gastrointestinal illnesses. However, there have been 3 coronaviruses in recent history that have caused serious diseases: SARS in 2003, MERS in 2012, and of course, the virus that causes COVID-19, SARS-CoV-2. Now, this trend in and of itself suggests to me that COVID-19 is probably not going to be the last virus challenge that we're going to encounter. Now, viruses and along with other particles that are harmful to humans, are very small. We measure them in microns. A micron is 1/1,000,000th of a meter. And to put that in perspective for you, a typical human hair is typically between 60 and 120 microns in diameter. When the afternoon sun shines through the window and you can see those dust particles floating around in the air, those particles are in the 10 to 30 micron range. Now, that's the lower limit of the visible spectrum for the human eye under optimal conditions. Now, the actual SARS-CoV-2 virus is submicron in size. It's approximately 0.125 micron. That's 600 times smaller than the diameter of a human hair. Capturing a particle as small as a virus is a challenge, but thankfully, at least from a filtration standpoint, the virus is not spread by itself, but it's contained within respiratory droplets expelled by an infected person when they sneeze, cough, talk, or even breathe. These respiratory droplets range in size, but the consensus is that they average around 2.5 microns. Still, these are very, very small particles. Now, just a couple of months ago, the ASHRAE Epidemic Task Force updated their statement on the airborne transmission of SARS-CoV-2 to say, airborne transmission is significant and should be controlled. Changes to building operations, including the operation of HVAC systems, can reduce airborne exposures. So there's a legitimate concern over airborne transmission of this disease in buildings, and smart air filtration decisions can certainly mitigate that risk. Some of the key variables in the spread of the virus are the size of the droplet, the time the droplet remains in the air, and the distance from the source. And we've all heard about the 6-foot rule. The 6-foot rule is based on the assumption that it was the larger respiratory droplets, those greater than 5 microns, that were responsible for the majority of airborne infections. Droplets of that size are just too heavy to stay suspended beyond that 6-foot range. However, respiratory droplets come in a wide range of sizes. These smaller droplets are known as droplet nuclei, sometimes referred to as aerosols. The smaller they are, the longer they can remain suspended in the air. And several studies have shown that they can remain airborne well beyond the 6-foot zone. Now, the exact role droplet nuclei and aerosols play in spreading the infection is still unknown, but the potential for these smaller droplets to recirculate through the air handling system means that we have to do our best to capture as many of these particles as possible. And we can't accomplish that through proper air filtration. Now, here we see a scale of particle sizes for various viruses, bacteria, and droplet nuclei. We see the actual COVID-19 virus there at 0.125 micron. But as we mentioned earlier, the virus is not viable on its own. Our target is the droplet nuclei and aerosols carrying the virus through the air. And while these targets are still very small, from an air filtration point of view, they are large enough to be confidently captured with high efficiency air filters. A MERV 15A or 16A filter will capture 95 to 100% of these particles. Now, many illnesses and diseases other than COVID-19 are spread by respiratory droplets and aerosols. As a result, the size and dispersion of human exhaled droplets is something that has been extensively researched. So while we don't know what the infectious dose of COVID-19 is, we do know that a starting point of 0.5 micron is the smallest aerosol particle potentially capable of containing a sufficient quantity of viruses to be considered a risk. Now, that's the small end of the scale. As I mentioned just a minute ago, the larger end of the scale are those droplets large enough to drop within 6 feet from the source. So between that low end of 0.5 micron and the high end of, say, 5 micron, the peak distribution analysis shows a mean particulate size of roughly 2.5 microns. So an air filtration solution with a capture efficiency of 95% or better within this particulate range would be a sufficient risk mitigation strategy. Now, air filters play a vital role in HVAC systems. Some filters, by virtue of the medias they use, fail to maintain the rated efficiencies over their service life. This drop in efficiency allows more of our targeted particles to recirculate back through the system and potentially infect others that aren't even in the same room as the infected person. In comparison, selecting filters that maintain their efficiencies throughout their service life shows that we can effectively mitigate that potential risk and maintain the desired indoor air quality. So what air filter efficiency options do we have? And what are some of the things we should consider when selecting appropriate filters? Well, in 1999, ASHRAE replaced the old 52.1 dust spot test method with 52.2, also known as the MERV test. Now, MERV stands for Minimum Efficiency Reporting Value. I'm sure many of you are familiar with filters being referred to as, say, a 45% filter or a 95% final filter. Well, this terminology is a holdover from 52.1, and it's been obsolete for over 20 years. As a matter of fact, if you are using 95% filters in a healthcare facility, these are not ASHRAE compliant filters for healthcare. Filters used in healthcare must have a MERV rating, and manufacturers must comply with the full 52.2 test standard in order to use the term MERV on any of their products or in their literature. Now, the 52.2 MERV test, what we're basically doing is just measuring particles in versus particles out. What we do is we introduce particles of 3 different size ranges to a filter, and we record the capture percentage in each of the 3 particulate ranges. Based on a filter's performance, we then assign a simple numerical MERV rating to the filter from 1 to 16. A MERV 1 rating being not very efficient, and a MERV 16 rating being a filter that is very efficient at capturing the smallest particles. Now, the particle capture efficiency of an air filter is primarily determined by the media. The filter configuration, yes, definitely plays a role as well, but it's the media itself that has the biggest impact on efficiency. And there are 2 basic types of media used in the air filtration industry. It essentially comes down to a comparison between fine fiber and coarse fiber. Fine fiber filters, like the image on the top here, capture particles through mechanical principles. Think about a fly running into a screen. The other type of media is a coarse fiber media that relies on an electrostatic charge imparted onto the media fibers for its efficiency. Now, at first glance, you say, there's no way this coarse fiber media down here is going to capture as many of these little red dots as the fine fiber up here on the top. But these 2 filter medias both test to the same MERV rating, at least initially. You see, when you first install electrostatically charged filters, the charge acts to attract fine particles to the media fibers. This allows the filter to achieve its initial MERV rating under the 52.2 test. But after a short period of time, enough small particles have been attracted to the media fibers that they create a barrier and they insulate the charge on the media. As a result, those small particles can now easily pass through the big openings in the coarse media. Now, this loss in efficiency is often 2 or more MERV ratings. So an electrostatically charged MERV 14 filter typically only performs at about a MERV 12 level. Now, it's important for me to note here that Camfil manufactures filters utilizing coarse fiber electrostatically charged media. There are certain applications or circumstances where an electrostatically charged filter might be an appropriate solution, but never in a healthcare environment. Now, this is a picture of an actual 52.2 test rig at one of our North American manufacturing facilities. In 2007, the ASHRAE 52.2 committee recognized this degradation of efficiency in filters relying on electrostatic charged media in order to obtain their MERV ratings. And they responded by introducing Appendix J, also known as the MERV A test. Appendix J is a supplemental test wherein we add a conditioning step. What we do is we introduce a potassium chloride aerosol to the filter media. This neutralizes any electrostatic charge that may be present on the media. We then subject the conditioned filter to the exact same 52.2 test. So now filters have both a MERV rating and a MERV A rating. The MERV A rating, or as I like to call it, the MERV actual rating, tells you how a filter is actually going to perform over its entire service life. When selecting air filters, you should always base your decisions on MERV A values. This is particularly true in healthcare environments where we're concerned with removing these small, dangerous particles. Now, this slide illustrates the critical nature of MERVA values. Now, for most spaces in healthcare facilities that require high efficiency filters, the minimum requirement is a MERV 14. And here we're looking at MERV test and an Appendix J test for a typical electrostatically charged MERV 14 filter. You see the filter here tests out to a MERV 14 on the initial 52.2 test. But on the right over here, when the Appendix J conditioning step is introduced, we see that the same filter drops in efficiency to a MERV 12A, very typical. And when you look at the test results over here, you can see the percentages of particles captured in the critical size ranges for respiratory droplets drop from a 78% all the way down to 26%. Well, that's a huge drop off. This is a filter that has absolutely no business in a healthcare facility. Now, in comparison, here are the MERV and MERV-A test reports for a fine fiber filter relying on mechanical principles for particle capture. You can see the MERV and MERV-A tests are the same. This is a filter that will perform at a MERV 14, 14A for its entire service life. And again, looking more closely at the performance of the filter in the critical ranges, there's virtually no drop off between the two tests. This would be an acceptable filter for mitigating risk against virus contained within respiratory droplets and droplet nuclei. Now here we have a comparison between MERV and MERV-A capture efficiencies for high efficiency filters. Again, as we look at our risk zone, you can see that there's a dramatic drop off in efficiency at every MERV level between the MERV-A and the standard MERV ratings. If our intention is to create a safe environment in our facilities, we have to look at MERV-A values. Besides, we all want to get the value for what we paid for. If you paid for a MERV 14 filter, that filter should deliver MERV 14 efficiency for its entire service life. So again, the way we ensure that is by making filter selections based on MERV-A values. Now, I want to talk a little bit about ASHRAE 170, the ventilation of healthcare facilities. The 170 standard details the minimum filtration requirements for healthcare facilities. It's published on a 4-year cycle in conjunction with the Facilities Guideline Institute Handbook. The 2021 publication of ASHRAE 170 was just released this last March. And I encourage everyone on this call who's involved at all in healthcare to get a copy. It's available through the ASHRAE website in both printed or electronic format. The 170 committee meets on a regular basis in an effort to continually make improvements to the standard in between these 4-year publication cycles. The changes are released in the form of addenda. And last fall, there were several addenda to the 2017 publication. Most significant among them was Addendum A. And the changes brought with Addendum A have been incorporated into the ASHRAE 170-2021 document. And there were 2 major changes that came with Addendum A. The first is that the old table 6.4 has now been replaced by 3 separate tables. Table 7.1 lists the minimum filter requirements for inpatient facilities. Table 8.1, and they've actually added a 8.2, address outpatient facilities, and table 9.1 for residential facilities. Now, the new tables are much more comprehensive and detailed than table 6.4 was, so they offer much more clarity with making filter decisions. The other big change was the addition of Appendix C and its associated notes. Now, in the 2021 version of the standard, Appendix C was renamed Appendix D, but the content remains the same. Now, I won't go into details of the tables here, but I do want to comment on Appendix D. It's a very handy Cliff's Notes summary version of what's contained in the tables. What it does is it narrows down filter efficiencies by space into 4 levels based on the minimum MERV requirement. Level 1 is for spaces that require MERV 8 filtration. Level 2 for spaces requiring MERV 14 efficiency. Level 3 is for spaces requiring MERV 16 efficiency. Now, this is a change. This is an upgrade from the 2017 standard and previous standards. Prior to 2021, standard operating rooms only required a MERV 14 filter. So there is an upgrade there. There are several upgrades in filter requirements in the new standard. And of course, level 4 addresses spaces in healthcare facilities requiring HEPA filtration. But what the most interesting thing to me about Appendix D can be found right down here in the notes below. And I know that's kind of small, so I'll blow it up for you. What it says is that where listed, MERV rating is assumed to be non-degrading. Well, guess what? ASHRAE 52.2 Appendix J is the only test we have to demonstrate non-degrading air filters by virtue of their MERV A values. So while MERV A values aren't explicitly required in the new standard, MERV A values are certainly implied. Canada has required MERV A values in healthcare for some time now. And most of the rest of the world follows the ISO standard, ISO 16890. The ISO standard includes a conditioning step very similar to Appendix J. So this is clearly the direction we're heading. Now, hopefully, I've driven home the point that filter selections based on MERV A values are critical in mitigating risks and ensuring safe indoor air quality. But there's another side to this as well. Filter performance also dictates operational costs. And here we see high efficiency filters in different configurations. These are all MERV A filters. Now, the replacement costs for filters increase as we increase efficiency. You can expect to pay more for a MERV 16 filter than you would for a MERV 14 filter. You can also expect to pay more for a 4V style filter like this one here than you would for a pocket filter, even at the same MERV value. So you might be thinking, well, you know, we're cost conscious here. These two filters, the 4V and the pocket filter, both have the same MERV rating. Let's go with a less expensive filter. But because the 4V style filter, when paired with the exact same pre-filter, has a lower average pressure drop, it consumes less fan energy. So electrical costs are lower and the lower total cost of ownership. So it's the performance of the filter that determines overall costs. You know, how long is the filter going to last? How much electricity is it consume? These factors are far more impactful than the actual replacement cost of the filter itself. Now, the fan energy required to maintain airflow across the filters is the single largest cost component of any air filtration program. And guess what? Those coarse fiber electrostatically charged filters, well, they load much more quickly than the high performance filter. So here we see the blue line representing the loading curve of a typical electrostatically charged filter. The flatter green line beneath it shows the loading curve of a fine fiber filter. Now, the difference between these two loading curves is your opportunity for operational savings. Sometimes the energy savings alone can be greater than the entire existing filter spend. It's like getting your filters for free. Now, I want to give you an example of how filter performance impacts operational costs. Something as simple as a pleated filter can make a huge difference. Now, this is a MERV chart. And a true MERV 8A or 9A pleat is going to capture a minimum of 70 to 75% of the particulate in this E3 range. Now, in the filtration world, that's the big chunky dirt. We're talking about particulate from 3 to 10 microns. Remember that lower range of the human eye spectrum is, you know, right around 10 microns. So, but to us, this is really chunky dirt. Now, if you look to the left over here into our critical range for respiratory droplets, you can see that this high performance pleat really isn't doing anything. But indoor air quality is not the job for the pleat. The primary function of the pleat is to protect the equipment. So let's say, well, again, we're cost conscious here, and you know, pleat's a pleat. Let's just go with our standard electrostatically charged MERV 8 pleat. Well, we know that that pleat's going to drop in efficiency, typically to a MERV 5A or 6A level. At this point, you are literally allowing twice as much of this E3 particulate to go right through that filter onto the coil. So what's that mean? Well, A prominent hospital out west that we work with made this switch to our dual 9 high performance pleat from a first cost solution. And after about a year, they came back to us and they told us that they were really happy they made the switch, that they had saved over $100,000 by doing so. And we said, "Wow, that's fantastic, but you got to help us with the math here a little bit because I think you only spent about $15,000 on pleats. How in the heck did you save over $100,000?" And their response to us was that they had budgeted every year for coil cleanings because they needed it. So much dirt was going through that cheap pleat onto the coils that they required cleaning every year. But it came around that year for them to schedule the cleanings, and they looked at the coils and they said, "You know what? They look beautiful. There's absolutely no reason we have to do this." So they were able to forego that expense completely. And this is something that very few people even consider when they're comparing something like a pleated filter, but it can have a huge impact. And along those same lines, the Train Company did a study some time ago on scaling, and they found that just a few hundredths of an inch of buildup on the coil can reduce the heat transfer capability of the coil itself by upwards of 30%. So let's take a step back a minute here and examine the inexpensive first cost pleat. It doesn't last very long. You're going to change it 2, 3, 4 times as often as a performance pleat. So your raw filter spend isn't going to be any less. It might be more than the high performance pleat. It's certainly going to be more expensive if you account for the additional labor involved for those extra changes and disposal costs. The cheap pleat consumes more fan energy due to its higher resistance and steeper loading curve, so your electricity bill is going to be higher. It necessitates more frequent coil cleanings, which negatively impacts your maintenance costs. And it can come with an additional energy penalty due to lost coil efficiency. Cheap filters are almost always your most expensive option. And this example is just with pleats. The same principles hold true for final filters, just on a larger scale. So I want to talk about HEPA filters for a moment here. HEPA filters have extremely high particle capture efficiency on submicron size particles. We don't rate them using the MERV scale. HEPA filters are tested for capture efficiency on particles 0.3 micron in size. This is the most penetrating particulate size for a HEPA filter. And they range in efficiency from 99.97% to 99.9999%. Now, there's the phrase true HEPA is something that's used pretty loosely, but it's not an actual technical term. But if we were to define it, a true HEPA would sound something like this. A true HEPA is one that has been individually tested to either the IEST recommended practice for HEPA filters or ISO 29463. A true HEPA filter is one labeled with the individual scan test for that actual filter. No batch testing, not estimates based on component tests, but the tested performance for each specific filter. Now, COVID-19 created a massive demand for HEPA filters. I remember one prominent politician calling for HEPA filters in all shopping malls. As you know, you can't just run around replacing ASHRAE filters with HEPA filters in an attempt to contain these kinds of threats. You need to have adequate depth in your system to accommodate a HEPA filter. You have to have the proper hardware and sealing to ensure there's no bypass. And your system needs to be able to handle that extra fan capacity required of a HEPA filter. But thankfully, there are supplemental solutions available that can deliver true HEPA indoor air quality to areas where existing equipment and cost-effective re-engineering alternatives aren't feasible. Small portable indoor air cleaners like the City M here in the middle can deliver operating room indoor air quality along with molecular level filtration for smaller spaces. There are also larger units available that not only act as in-room air purifiers, but can also be adapted to exhaust HEPA filtered air out of space and create a negatively pressurized room. So wrapping things up, viruses and other dangerous particles we encounter are very small. But with proper filtration with high efficiency filters that maintain those efficiencies, we can effectively capture them. The key here is on insisting on filters with MERVA values. If there's one thing you take away from this presentation today, that would be it. In healthcare, really anywhere where we're concerned with indoor air quality, we need to be selecting filters based on their MERV-A values. How we do this? You ask your supplier for the full 5-page 52.2 test reports along with the Appendix J reports for every filter type you have on site. If your supplier's unwilling or unable to supply with this documentation, well, that might be an indication that it might be time to start shopping around for a new vendor. Evaluate your filter choices based on performance. Across the country, for every dollar a hospital spends on filter replacements, they're going to spend $7 in operational costs. It just makes common sense that if you're looking to reduce cost, focus your attention on the areas where you stand to realize the greatest savings. And keep in mind that there are portable air purifier and air cleaners that can be great solution to deliver the necessary indoor air quality to spaces in your facility. Okay, now that's the end of the presentation portion. This is my contact information. Feel free to reach out to me. We're going to now segue into a Q&A session. But if we don't get to your question, please reach out to me directly. I'll either answer it myself or I'll funnel it to the person who is best suited to answer your question. But before we get into the Q&A, I'd like to hear a little bit from a couple of our panelists here. I'll start with you, Richie. You've been on the front lines throughout this pandemic. Share some of the obstacles and challenges you faced over this past year and how you were able to overcome them.
Yeah, thanks, Kyle. So again, my name is Richie Stevens. I'm the Director of Facilities for University of Maryland Medical Center, both downtown and midtown campuses. I'm just giving you background of what I was doing. That is a hospital. The main hospital is 800 beds, 2.5 million square feet. And the smaller hospital is 1 million square feet and 250 beds. So a lot of real estate. Here in Baltimore, we were about 2 weeks behind the New York spike. We saw the virus coming across the country, started on the West Coast, hit New York pretty hard. And we recognized our numbers based on our trends. We were right behind New York. So we did a quick evaluation of not only my 2 hospitals, but the rest of the 13 hospitals in the University of Maryland Medical System portfolio to determine air filter efficiencies, capacity to house the COVID patients, both positives and those under investigation. And we also recognized, based on CDC literature, that we needed to create negative spaces, negatively pressurized spaces for appropriate housing of these patients. So naturally, we did evaluation of the negative rooms. We determined that we needed more. So we brought in portable units. Most of them we exhausted through the window, and we did have 99.95% HEPA filters, not ULEPs, but standard HEPAs on those units, even though we're exhausting directly to the outside, not near an intake, not at street level, but we did want to make sure that we filtered out that particular before we send it outside. A lot of the air handlers in the main building are 100% outside air. So we're bringing in outside air, filtering and those particular units have HEPA filtration on it, and filtering it, then distributing it through the building, the clean air, and then dumping it back outside. Where we did have some air handlers that recirculated, we evaluated the MERV rating. And from a report that we received early on, essentially halfway through the pandemic, that identified that MERV 16 was the ultimate filtration choice for mitigating the risk associated with this virus. We evaluated some of the air handlers to determine whether we could upgrade from a 14 to a 16. And we took into, as your presentation alluded to, Kyle, we looked into the fan efficiency, the ability to withstand the filter drop based on the numbers from the air filter, the posted numbers for the air filter. Weight was also a concern. We recognized changing MERV ratings sometimes brings in a heavier filter array. And again, I'm talking about big air handler systems, that 100,000 CFM with big filter banks. So the pressure drop, the weight, and the overall configuration were of concern to us. So we were able to make some changes to several of the air handlers going from MERV 14 to MERV 16. And we felt much better about providing a clean environment for our patients, staff, and visitors. So that's just a little background on what we did. There was a lot of discussion in this industry about UV. There was not enough data to support the addition of UV. So we just focused our efforts on filtration.
Thank you, Richie. You certainly had your hands filled. It sounds like you made all the right moves. So great job. Kim Shin, principal and a senior director of sustainability at TLC Engineering. Kim, nobody really knew what to do when COVID first hit, and understandably reactions were all over the map. Would you tell us about some of the reactions you had from clients and how you advised them through all this craziness?
In much the same way that Richie responded with some of the things that he did, we saw a lot of our clients taking similar measures. And because we really didn't, in the early days of the pandemic, understand how much of the virus was being distributed via aerosols, how much was the droplet nuclei, how much was surface contact, that's where we got all of this information about washing our hands in the 6-foot distance. We also weren't particularly knowledgeable about how long the virus would survive once it was out in the air. And as Richie explained, a lot of people took the step of exhausting 100% of the air from these patient rooms. And while an airborne infection isolation room is required to be 12 air changes per hour, maintained at negative pressure to the adjacent space, and fully exhausted through basically a hazardous exhaust system, we just weren't able to do that with all the patient rooms that were being occupied by COVID patients. So the first reaction was, let's open up basically the windows and blow air right out of the build out of many more patient rooms than the air conditioning systems were designed for. Luckily, this was happening in the springtime when our air conditioning systems could handle the additional outside air load. It wasn't too cold, it hadn't gotten too hot and humid yet, and we were able to, especially in areas that are used to doing economizers, handle that additional outside air going through our air conditioning systems. But it soon became obvious to a lot of our owners that their air conditioning systems just would not handle that. And by that time, we had gained more knowledge about the diameter of the droplet nuclei that we were having to deal with. We had a much better handle on how much of the transmission was aerosolized, airborne transmission. And it became really plain to us that we didn't need to really go to these extraordinary lengths of going to 100% outside air. We wanted to reserve those spaces that were 100% outside air for doing aerosol generating procedures. So bronchoscopies, intubations, the things that were really inducing a whole lot of virus out into the space. We wanted to reserve rooms that were 100% outside air for those. But simple patient rooms, even though they had COVID patients in them, could really be recirculating room. And we found that given the MERV-13 and MERV-16 final filters that are serving most of our patient rooms, that we were able to basically interrupt the pathway of transmission. Another thing that was counterintuitive was we had a lot of our hospitals come back to us and say, we need to isolate everybody that's got COVID so we can put them all in one air handling system. And that was a guess of what might happen, thinking that if we've got infected patients in this area that's being served by one air handling system and something bad gets back through the air handling system and back into, it will just go into spaces that are already containing infected patients. But it turns out that once again, the filtration was good enough to interrupt that transmission. In fact, to date, we have 0 documented cases of infection going through a properly operated, up to code, multi-zone air handling system. The standard 170 has served us very well in this pandemic. Now, there's been person-to-person transmission inside spaces that are standard 170, but no transmission between spaces where that air has circulated through a multi-zone air handling system. It turns out that the multi-zone air handling systems actually not only have the filtration going for them, they have a lot of dilution going for them. We also got a lot of questions about, can we turn one of our operating rooms into a negative pressure space? Because we're going to have COVID patients that we have to operate on in operating rooms, and we don't want any of those bugs getting out of there, because as operating rooms have to be positively pressured. It turns out that the air change rate in operating rooms is so high that the dilution factor associated with the just normal business as usual in an operating room, even though that space would be positively pressured, the amount of virus that would escape out of the door, under the door cuts into the adjacent corridors, is less than what's required for an infection. So there's the big lesson that we got out of this was, don't distrust the air conditioning ventilation systems that are in hospitals that are up to code, properly operated. That this is probably the safest environment in North America for an airborne infectious disease. Now, it's a problem that we got a bunch of sick patients in the spaces, and when you go into the same space with them, you can be infected. But generally speaking, the air conditioning systems in North American hospitals are of such high quality that we see very little airborne infection transmission in those spaces. And doing things like changing your air balance to introduce more exhaust just will mess things up. Trust your filtration systems, trust your air handling systems to keep you safe.
Excellent, excellent. Thank you, Kim. Shall we turn it over to Lynn? Are there any questions out there that the people would like to have answered?
We do have a few questions in the chat. There's the first question: is there an average time period that the electrostatic charge is depleted? Are we talking hours, days, weeks?
Evan, you want to grab that?
Yeah, I'd be glad to take this one. Both prior to ASHRAE in 2007, adding the conditioning step as Appendix J and creating the MERVA value report, we have done literally thousands of tests in the field of charged synthetic medias versus charged fiberglass medias to look at how long does it take for the efficiency to be reduced in a charged media filter. And it is different from a pleated filter to a final filter. There are two things that typically dissipate the charge. One is humidity and the other is particle loading. So either one or both will reduce the efficiency of the filter. If it's a pre-filter or pleated 2 or 4 inch filter, because they have significantly less media than a final filter, when they're exposed to that air, normally their efficiency, if it's a charged media, will drop within a few days to a week. So if you take a filter that should, let's say, have a 3-month life that's rated as a MERV 8, it's probably going to be a MERV 8 for about 1 week, and the rest of that 3-month period, it's going to be at a MERV 5 or somewhere in that range. If you take a final filter, it takes a little bit longer for that charge to dissipate. It can take a few weeks, 30 days, it can take up to 60 days. But again, then you take a filter that's going to have a 12-month to a 24-month to a 36-month life that's rated at MERV 14, and it's going to operate at a MERV 12 during at least 80% of its life. So that's the experience we have in real life. The other thing I would say that we ran into a lot in consulting customers is there really are 3 things that you want an air filter to do. 1 is to maintain its efficiency. 2 is to have the lowest average pressure drop over its life, so you can serve the most energy. And 3rd is to have the longest life at that lower pressure drop, so you have the least cost for labor and disposal. So what we ran into in many cases, hospitals that were using poorly designed filters, either whether they were MERV 14, charged or uncharged medias, in many cases they could upgrade to a MERV 16 filter and still save energy and have longer life because the filters did not have a good average pressure drop to start out with or a good lifetime. So many times you can improve your system without having to pay a huge pressure drop penalty, and you can do it within the existing fan profiles and VFDs that you already have.
Okay, thank you. Next question, is it possible that a portable purifier and filtration system can be safely used in a little surgery room instead of a chiller system or divided system with filtration banks?
Kevin, you want to answer that one?
Yeah, as you probably all know, after COVID started, everybody that could build a box and put wheels on it and put a filter in it introduced a portable air purifier. So I think one thing you need to really look at is what is the quality of the product, and specifically what is the quality of the filter that's within that product, because that's going to determine the operating cost, the life. But if the product is well designed, there's no reason that it couldn't be used within most spaces within healthcare. Now, there are some requirements within an operating suite as far as what plug types you have to use and other electrical things, but certainly an air purifier can supplement any space. You just need to make sure that you select the right one that's going to fit the quality that you need and the performance that you need.
There's a couple other considerations. Velocity coming out of that box and its ability or inability to stir up dust. So we did some tests with portable units that had side discharge that were low to the ground. And as soon as we turned them on, the dust bunnies, we didn't know that they were there. The dust bunnies started flying in the air. And then also the proximity to the aerosol generating procedure or the area you're trying to protect. But generally those boxes are better at pushing air than pulling air. So that proximity, that ability to get it close enough to the area that you're trying to secure is another factor that has to be considered when you're doing that. And then how do you maintain required air exchange rates, outside air requirements, and the like?
Yeah, very good point, Richie, because typically with an air purifier, your ability to push the air, throw the air is about 30 times your ability to draw air in. So both whether that exhaust is at the top or the bottom or the side can have a big difference, as well as where it's placed in the room and at what fan rate or speed you might want to run that unit to balance everything out.
The size of the space is also a consideration.
And the next question is, are there any strong studies supporting ultraviolet chamber filtration that are able to clean air in a room?
The thing about UV is it is extremely dependent on dosage. And dosage is governed by how much residual time the particle will spend inside the kill chamber. And it's dependent on how much air is flowing through the chamber, how quickly it flows through the chamber, the intensity of the UV light inside the chamber. The simple response is that UV is actually a good supplement inside an air handler for keeping coils clean, but filtration and dilution are much more effective in providing the kind of cleanliness that is required in standard 170 than UV is. I would call UV the suspenders that you would add to your belt. But there's simply no compelling evidence that you would use UV lighting in place of filtration.
Tim, in addition to that, ASHRAE is developing a guidance document that should be published in the next couple of months about room side UV usage and their recommendations. So look for that.
So there was an add-on, but I think you answered it. So do you think it is better to use UVC lamps or filters or both? So I believe.
My opinion is filters.
I agree.
Okay, thank you. Okay, next question. Will you please discuss best practices for dealing with smoke during wildfire season on the West Coast?
MERV 13s in your outside air intake.
Yeah, it's one of those things that smoke it's best treated through molecular filtration from the odor standpoint. Of course, if you're in a fire season, you've got a lot of ash in the air. You've also got the issue of catching all that ash coming through. It's a matter, sometimes that odor is just something that you're not going to be able to 100% handle. With a pre-filter solution, there's just not enough molecular product in there in the media to really absorb it all. But it is your best bet. Kevin, you see it. We typically sell a lot of carbon filters during fire season.
Yes, we do. A lot of clients will put in carbon pleats in place of their standard pleats for a period of time. That's going to certainly allow the final filters to load, but that way it keeps the nuisance odors out of the inside of the building if the exposure to the fire is short term. If you're in a location where you're going to experience fires fairly close year after year, then you probably need to look at an additional stage of filtration in your system that might include molecular.
And I will add, we also did a video that's on our YouTube channel I can share in our follow-up. It was an interview with our molecular segment manager, and it was strictly on wildfires. So that might be helpful information for you as well. Next question, does the MERVA test take into account that the electrostatic filters become more efficient as they load with particles?
Well, that's a little bit of a misnomer there. There is some data that says that they do increase in efficiency at the largest particle sizes, but it's really minute. And overall, what you're going to find is, yes, the MERVA test will show you what that actual MERV rating is over time. Whatever small increase you're going to set is not it's not overcompensated for by the actual MERVA test. So I guess the answer to that question is no, there is no real gain in efficiency from a electrostatically charged filter.
Yeah, when those medias were first introduced, probably 25 years or so ago, the theory was that while it was thought that particle loading would insulate the electrostatic charge, that loading of particulate would eventually create mechanical filtration barriers enough to maintain the efficiency. But what happens when you really look at the fiber structure, a synthetic charged media has larger diameter fibers that are spaced further apart. So even when they load with particulate, there's still a lot of open spaces that let smaller particles pass through, and that's where the loss of efficiency and MERV rating occurs.
Okay, thank you. Next question. What option of negative pressure room can a hospital choose in managing COVID-19 patient in medical wards? Because it's so difficult to build anterooms in every isolation room.
Kim, you want to tackle that one?
Something that we've had a lot of success with is using a portable HEPA machine, placing the HEPA machine inside the patient room, and then having it discharge the world's cleanest air into the corridor. So what that does is it both increases the air changes within the patient room, and it creates the negative pressure relationship between the corridor and the patient room. So you've got the HEPA machine inside the patient room and then discharging out into the hallway. You got to take your nursing staff into consideration and say, HEPA filters were developed as part of the Manhattan Project. They were to protect people from nuclear radiation. That's how good they are at filtering. The air that comes out of a properly operated HEPA filter is cleaner than the air on top of Mount Everest. So you've got some education to go through. The thing about antirooms is, even if you are sucking 300 CFM through a 3.0 by 7.0 door, there is no pressure difference there if the door is open. If that door is open, there is no pressure relationship. People passing by in the hallway with an open door, even though it's got 300 CFM being exhausted out of it, will be infected by the stuff that's circulating inside that patient room. The door has to remain closed. So what antirooms do is basically improve the resilience of that pressure differential. Anytime that door is open, though, there is no pressure relationship between those two spaces. There's actually been a study showing of a nurse who was infected with chickenpox, even though she never entered the infected patient's room. She simply handed stuff through an open door to one of her colleagues in PPE, but that door being open allowed the airborne chickenpox virus to infect her.
What about bipolar ionization?
I don't know that any of us probably know enough to answer, but I guess my opinion would be there isn't enough scientific data to really judge whether it works or doesn't work and under what conditions, because most of the work that's being done hasn't been done with standard approved test methods. So I would say we just don't know enough at this point.
Okay, thank you. Next question. There is some chatter out there about using systems incorporating hydrogen peroxide. Any thoughts or discussion on that? I'm not talking about PCO.
Hydrogen peroxide is essentially an ionization strategy. What happens is the hydrogen peroxide breaks down into water and a hydroxyl molecule ion, and it's simply another ionization strategy. And as Kevin said, right now we just don't have enough standardization and real world experience with both the efficacy and the safety associated with those methods.
Okay, thank you. Any recommendation on design spaces and its adjacencies to support ventilation? Deep plan versus minimum standard for natural ventilation.
Anybody have anything on that one?
I'm not sure I understand the question.
Yeah, I'm struggling with the same thing. The way I understand it, you're looking for a way to design in flexibility. And I think what we learned from COVID is that, yes, we want to, as we build new spaces and renovate old spaces, we want to increase our ability to be flexible with airflow going from positive to negative, moving air this direction, that direction, to change in adjacencies as far as airflow is concerned. If I understand the message correctly, it's should we design in flexibility? And my answer is yes.
And the deep plan versus minimum standard for natural ventilation, that's an interesting comment. I think designing narrow floor plates for natural ventilation is a great resiliency strategy. If you are in a situation where you're not able to maintain your mechanical ventilation because of disaster or some other circumstances, then natural ventilation, the ability to open a patient room window and get air to circulate through that patient room, is extremely valuable. But it's certainly not at this point a code requirement to do that. I'm a big fan of operable windows. I'm a mechanical engineer. I may be the only one you ever find that says he's a big fan of operable windows, but I think it's a great resiliency strategy.
Okay, I think that is it. I want to give a big thank you to our speaker and our expert panel. There's a lot of valuable information that was shared today, and we definitely appreciate that. Before we conclude, I do want to let you know a recording from today's webinar will be available soon, as well as the presentation. Please do look out for a follow-up email with information on how to view the webinar. And again, thank you for attending today's webinar. Have a great day.
Thank you all.
Thank you.
Thank you.